All right, class, welcome. Today, we are going to take a classic engineering problem right out of the textbook and bring it to life. We're going to design, calculate, and, even troubleshoot a real-world device. This is where we turn all that circuit theory into an actual, tangible solution. And trust me, this is where the real fun begins.
So let's start at the end, shall we? This is what we're building. It looks pretty simple, right? Just a box with a knob to control a cooling fan. But the real engineering, the elegance of it, is what's happening on the inside. Our job today is to figure out the brains of this operation.
So how in the world do we get from one simple knob to 4 separate precise fan speeds? Well, the secret sauce here is actually just good old Ohm's law and a few really carefully chosen resistors. Our challenge, our puzzle for today, is to figure out exactly which resistors we need to use.
Okay, so before you even think about picking up a soldering iron, every single engineering project has to start with a clear set of requirements. This is our blueprint. Think of it as the list of demands from our client that's going to guide every single decision we make from here on out. And here is our basic schematic. It's beautifully simple, isn't it? We've got a 12-volt DC power source, our fan motor, that's the circle there with the M in it, and a series resistor, which we're calling R. The whole idea is that by changing the value of R, we control how much voltage and current gets to the motor, and that in turn controls its speed. Simple.
So here's the nitty-gritty. We're working with a 12-volt supply. The fan, when it gets the full 12 volts, spins at its maximum speed of 800 RPM. But our client wants options. They need 4 distinct speeds: 800, 600, 400, and 200 RPM. So our main task is to find the 3 resistor values that'll nail those lower speeds perfectly.
All right, now for the main event, the calculations. This is where we take those client requirements and we use the motor's own performance data to translate a target speed into a very specific resistance value in ohms. This, right here, is the absolute heart of the design process.
These 2 graphs, these are our keys to the kingdom. These are the motor's characteristic curves. You could think of them like the motor's unique fingerprint or its personality. They show us exactly how it behaves. On the left, you see how its speed changes with current, and on the right, you see how the voltage it needs relates to that exact same current. Everything we need is right here in these 2 plots. So we're going to follow a super logical 4-step process. First, we pick a target speed from our spec sheet. Second, we use that first graph to find out how much current the motor needs to hit that speed. Third, we hop over to the second graph to see how much voltage the motor needs at that current. And finally, we just use Ohm's law to figure out the resistor we need to burn off the leftover voltage from our supply.
Let's walk through one together. Let's aim for 600 RPM. So, looking at that first graph, 600 RPM needs about 0.18 amps. Okay, now, at that same current, the second graph tells us the motor wants about 8 volts across it. But remember, our supply is 12 volts, so our resistor has to use up the extra 4 volts. Now it's just Ohm's law. Resistance is voltage divided by current. So 4 volts divided by 0.18 amps gives us 22.2 ohms. Boom! Done! And you just rinse and repeat. You do that exact same process for our other target speeds, and you get this complete table. Now notice for 800 RPM, the motor needs the full 12 volts, so our resistance is 0. We basically just use a plain wire. For the other speeds, we have our nice calculated values. This table right here, this is now our parts list for the build.
Okay, we've got the numbers, our calculations are done. Now we move from paper to prototype. It's time to take those numbers and turn them into a real, functional circuit that actually brings our design into the physical world.
And here it is. This drawing shows the final design perfectly. That rotary switch is the real hero of the controller. As you turn the knob, it acts like a railroad switcher, connecting the power supply to the motor through a different path. Position 1 is a direct line, full speed ahead. But positions 2, 3, and 4 route the power through our calculated resistors, R1, R2, and R3, to give us those exact lower speeds we wanted. But here's a little dose of reality. In the real world, a perfect design on paper does not always mean a perfect first build. You get a cold solder joint, a loose wire, stuff happens. So, a critical part of being an engineer is knowing how to find and fix those problems. That's called troubleshooting.
So let's imagine a scenario that you will, I promise you, run into someday. You've built the circuit, you're all proud, you power it on, and doot! The fan only runs at its slowest speed. It doesn't matter where you turn the knob, it's stuck. Where would you even start looking for the problem?
Well, your best friend in this situation is always the multimeter. We can use it to measure resistance and basically go on a scavenger hunt for the fault. A really powerful technique is called half-splitting. For our circuit, that might mean checking the connection halfway through, say between the switch and the resistor for the medium speed. If that part's good, you know the problem's further down the line. If it's bad, you know the problem's before that point. You instantly cut your search area in half. It's a divide and conquer strategy.
Now, in our little stuck-on slow scenario, the usual suspect is something called an open circuit. It's just a fancy term for a break in the connection. If the wire that's supposed to lead to the higher speed resistors is broken, well, the current just can't get there. If you put an ohm meter across that break, it'll read infinite resistance and it'll point you right to the problem.
So, you see, the big takeaway here is that design, building, and troubleshooting are all part of the same loop. They're totally interconnected. Which leads me to a final thought for you. Now that you've seen this whole process, how would you write up a formal test procedure to guarantee this controller works perfectly before you ship it off to the client? Answering that, well, that's the final piece of the engineering puzzle.